In previous lecture, we have seen that in a RLC series circuit, when the resistance is very low, then during resonance, the resonance curve is very sharp, and this is considered as the highly selective circuit. On the other hand, when the resistance of the RLC circuit is very high, then the resonance curve becomes flat, and this is said to be the low selective circuit or low selectivity. So here the selectivity of different resonance circuits are compared in terms of their bandwidths. So let's see the concept of the bandwidth, and first its definition. So bandwidth is defined as the range or the bands of frequency which lies between 2 points on either side of the resonant frequency, where the current is 1 by root 2 times of the maximum current. Remember one thing here, the maximum current means at resonant frequency when the impedance becomes minimum, that is equal to resistance, then the circuit current becomes maximum, that is V upon R. So the definition of the bandwidth states that it is the range of frequency which lies between 2 points on either side of the resonant frequency where the current is 1 by root 2 times of the maximum current. Now see this figure. Here I have drawn the resonance curve, that is the current in a RLC series circuit with respect to the frequency. So in previous lecture during graphical representation, we have already seen that the nature of the current with respect to the frequency makes this type of characteristics, and this is called the resonance curve. Here in the resonance curve at FR, that is the resonant frequency, the current becomes maximum and Imax is V upon R because the Z is equal to resistance. Now if we consider the 1 by root 2 times of the maximum current, then definitely the value will be lower than the Imax. Let's say this is the current Imax upon root 2. So in this current, we can get the current in two different frequencies that can be seen from the resonance curve. That means in this frequency, that is at F1 as well as at the frequency of F2, the value of the current will be Imax by root 2. Therefore, the range of F1 and F2 is considered as a bandwidth. So the bandwidth is defined as the del F, and it will be F2 minus F1. So let's see the definition. Bandwidth is the range of frequency lie between 2 points on either side of the resonant frequency where the current is 1 by root 2 times of the maximum current. So this is the bandwidth. Now in the bandwidth, as we have seen that the current is Imax by root 2. Now when the frequency is equal to the resonant frequency, that is FR, in that case the current is Imax, where I have written Imax equal to V upon R. So in this case, what will be the power of the circuit? So the power of the circuit will be Imax square into R. So this is the maximum power that we can obtain at resonance condition. This is at FR frequency. Now when the current is Imax by root 2, so the power will be Imax by root 2 square into R. it is at f1 frequency. So here we can write I max square by 2 into R, and it can be rearranged as 1 by 2 of I max square into R. So we can write P1 is equal to half of P max. What is P max? P max is the maximum power that we will obtain during resonance, that is I max square into R. This is the maximum power. In a RLC series circuit, we cannot get the power more than this value. So this is the power at resonant frequency. So when the current is I max by root 2, in that case the power will be equal to half of the P max. Similarly, if we want to find the power at F2, in the same process, we will get the P2 is equal to half of P max. That means at FR frequency, the power of the circuit will be maximum, but at F1 and F2, the power will be half of the maximum value. That's why these F1 and F2 are called the half power frequencies. So in the bandwidth, the range of frequency lie between 2 points, that is F1 and F2, and this F1 and F2 are called the half power frequencies, where F1 is called the lower half power frequency and F2 is called upper half power frequency. So the bandwidth lies between two half power frequencies. F1 is the lower half power frequency and F2 is the upper half power frequency. So there are some points for the bandwidth and the half power frequencies. So we can point one by one. So at F1 and F2 frequency, the current is I max upon root 2, where I max is equal to V upon R. So the impedance of the circuit at F1 and F2 should be equal to root 2 into R. Here, how can I get this? You can see that I max equal to V upon R. I max is equal to V upon R. Now if I want to get the I max by root 2 current, so if I divide the I max by root 2, then in this side also you have to divide by root 2. That means when the current is I max by root 2, in that case the value of the impedance will be root 2 into R. The value of the impedance will be equal to root 2 into R. This is the magnitude of the impedance. It is only the multiplication of the resistance by root 2. The magnitude of the RLC series circuit impedance should be equal to root 2 into R. The next point that you have to remember that F1 and F2 are called the half power frequency that we have discussed just right now. So here the power is half of the maximum power. And the phase angle of the circuit, that is phi, will be equal to 45 degree at the half power frequencies, that is at F1 and F2. So now let's find the value of the bandwidth and the half power frequencies. So we have discussed here, we have discussed here the Z is equal to root 2 into R. This is the value of the impedance at half power frequencies. But in a RLC series circuit, we have already know that the impedance is the square root of R square plus XL minus XC whole square. So this is the impedance of the RLC series circuit that we have already know. And from this condition, Z is equal to root 2 into R, we can write square root of R square plus XL minus XC whole square is equal to root 2 into R, or square both the sides, so it will be R square plus XL minus XC whole square, and here it will be 2R square, or XL minus XC whole square should be equal to R square, because 2R square minus R square, so it will be R square. So XL minus XC will be equal to plus minus R. So here this is the relation of the reactance at half power frequency. Remember, this relation is obtained at half power frequencies, that is at F1 and F2. Now here the value of XL minus XC may be either plus R or it will be minus R. That means XL may be greater than XC, or sometimes XL may be less than XC. If we remember the graphical representation of the resonance curve, there we have discussed that if the frequency is less than the resonant frequency, then the XC is greater than XL. So the circuit is resistive capacitive in nature. And if the frequency is greater than FR, that means the supply frequency, here the frequency means the supply frequency, then XL is greater than XC. It means the nature of the circuit will be resistive inductive. And when the frequency is equal to FR, then XL is equal to XC. So the circuit becomes purely resistive, and this is called the resonance. So here we can see that from the resonance curve, we have already seen that F1 is lower than the resonant frequency. So at F1 frequency, the nature of the circuit will be capacitive, because here XC will be greater than XL. And at F2 frequency, which is more than the resonant frequency, here the XL will be greater than XC. F1 is lower than the resonant frequency, so in this point the capacitive reactance will be more than the inductive reactance. And F2 is higher than the resonant frequency, So here the inductive reactance will be more than the capacitive reactance. Therefore, we can write XL1 minus XC1, that is at F1 frequency, the value will be minus R. This is at F1 frequency. And similarly, XL2 minus XC2 will be equal to plus R. This is at F2 frequency. At F1 frequency, the capacitive reactance is more than the inductive reactance, so the value will be negative. And at F2 frequency, that is the frequency more than the resonant frequency, here the XL will be greater than XC, so the value will be positive. Now, XL1 can be written as 2 pi F1L, or it can be written as omega 1L. XC1 can be written as 1 upon 2 pi F1C, or it can be written as 1 upon omega 1C. Similarly, XL2 is 2 pi F2L or omega 2L, and XC2 is equal to 1 upon 2 pi F2C, or it is 1 upon omega 2C. Therefore, the omega 1L minus 1 upon omega 1C is equal to minus R. Let's say this is equation number 1. It is at F1 frequency. And similarly, omega 2L minus 1 upon omega 2C is equal to plus R. Equation number 2, and it is at F2 frequency. Now from equation number 1, if we simplify this, then it will be omega 1 square LC minus 1 upon omega 1C is equal to minus R, or LC omega 1 square minus 1 equal to minus RC omega 1, or LC omega 1 square plus RC omega 1 minus 1 is equal to 0. So omega 1 is equal to minus RC plus minus square root of RC square minus 4A into C. So it will be minus LC minus 4LC into minus 1 upon 2A, that is upon 2LC. So if we simplify this, it will be minus RC plus minus square root of RC square plus 4LC by 2LC. Now put this value into the square root, divide this value by 2LC, so it will be minus R upon 2L plus minus, if we make it within the square root, so it will be RC whole square upon 2LC whole square, so it will be R upon 2L whole square plus 4LC upon 4L square C square, so it will be 1 upon LC. So this is the value of omega 1. Here we can see that we will get two different values for omega 1. One is for the plus and another is for the minus. But if we take minus value, that means the value of omega 1 will be negative and it indicates f1 will be negative. But frequency cannot be negative. It is not possible the frequency to be negative. Therefore, we can ignore the negative sign. So finally, the value of omega 1 is equal to minus r by 2l plus square root of r by 2l whole square plus 1 by LC. So this is the value of omega 1 that we have obtained from the relation. Now the second equation that we have already written here, omega 2 L minus 1 upon omega 2C is equal to plus R. So from equation 2, in the same process, that is omega 2L minus 1 upon omega 2C is equal to plus R. So in the same process, if we simplify this, we will get the value of omega 2 as R by 2L plus minus square root of R by 2L whole square plus 1 by LC. We can show also by simplifying this equation, and finally we will get this value. And again here we will ignore the negative sign, because if we consider the negative value, then the value of the omega 2 will be negative, and this is not possible. Therefore, the omega 2 will be equal to R by 2L plus square root of R by 2L whole square plus 1 by LC. So this is the value of the omega 2 that is at the upper half power frequency. Now find omega 2 minus omega 1. So the omega 2 is R by 2L plus square root of R by 2L whole square plus 1 by LC. Whereas the value of omega 1 is minus R by 2L plus square root of R by 2L whole square plus 1 by LC. So the second term is similar. And the first term, it is R by 2L and it is minus R by 2L. So if we subtract omega 1 from omega 2, it will be R by L only. Because this is omega 2 minus omega 1. So minus minus it will become plus and it will become minus. So these two values will be cancelled. So finally omega 2 minus omega 1 will be equal to R by L. And the value of omega 2 is 2 pi f2 and it is 2 pi f1, and that is R by L. So finally we can write f2 minus f1. If we take 2 pi common, then it will be R by 2 pi L. Therefore, the bandwidth, that is del f, it is equal to f2 minus f1, and its value will be R by 2 pi L. That is the expression of the bandwidth. Now if we see the resonance curve once again, So here f2 minus f1 is bandwidth, so this will be del f. Therefore, if we want to find the value of f1 and f2 in terms of resonant frequency and the bandwidth, then the f1 can be written as fr minus del f by 2, and f2 can be written as fr plus del f by 2. So now the lower half power frequency, that is f1, and it can be written as fr minus bandwidth, that is del f upon 2, and it can be written as fr minus r by 4 pi l. So f1 is fr minus r by 4 pi l. This is the value of lower half power frequency. And similarly, the upper half power frequency, that is f2, can be written as fr plus del f by 2. So it will be fr plus r by 4 pi l. So finally f2 will be fr plus r by 4 pi l. This is the expression of the upper half power frequency. Now it can be also seen that if we multiply f1 and f2, then it will be the value of square of the resonant frequency. In other words, the fr can be also represented as the square root of f1 and f2. So it can be also possible, where fr is the midpoint of the resonance curve and it is the midpoint of the bandwidth. So here is the value of fr. So in other words, we can also write fr can also be written as f1 plus f2 upon 2. So that is also can be written. Now see the quality factor. Before we discuss about the quality factor, here is the RLC series circuit. V is the voltage supply and the circuit is running at a resonant frequency, that is fr. So we know that during resonant frequency, during resonance condition, the circuit current becomes maximum. So the maximum current will flow through each and every element of the circuit. The voltage drop across the resistance VR, it will be equal to the supply voltage at resonance, and this will be I max into R. So during resonance, the supply voltage will be equal to voltage drop across the resistance, and it will be equal to I max into R. Now the voltage drop across the inductance and voltage drop across the capacitance, these two values will be equal but opposite, so they will cancel each other. But if we want to see the magnitude of the voltage drop across inductor or across the capacitor, so we can see that the value is much greater than the supply voltage. So during resonance in a series RLC circuit, the voltage drop across inductor or across the capacitor may be greater than the supply voltage. Therefore, here the voltage is magnified. That's why the series RLC circuit is also called as the voltage magnification circuit. So RLC series circuit is also called as voltage magnification circuit. And as the voltage is magnified here, so the series resonance is also called as voltage resonance. And one point is, as the maximum current is allowed to flow through the circuit during resonance, so this circuit is also called as the acceptor circuit. So RLC series circuit is also called as the acceptor circuit. So these are the various definitions and their relations. But in quality factor, as we have seen that during resonance, the current flow through the circuit is maximum. Therefore, the voltage drop across the inductor or across the capacitor will be greater than the supply voltage. So, the value of the point by which the voltage is magnified, this is considered as the quality factor. So, the quality factor is defined as the ratio of the voltage drop across inductor to the supply voltage, or it can be also written as the voltage drop across capacitor to the supply voltage. Therefore, quality factor is the factor which indicates the magnification of the voltage in a RLC series circuit during resonance condition, and this magnification will be occurred across the inductance or across the capacitance. Now, if the voltage drop across inductance is very high, then this voltage drop can be used as a source for some another circuit. So here the voltage is magnified during resonance condition, and quality factor indicates how much amount of voltage is magnified compared to the supply voltage. So it is just a ratio, it is VL upon V. Let's try to find the value. As we know that during resonance condition the current is maximum, so the VL will be equal to I max into XL, and V will be equal to the voltage drop across resistance, and it will be I max into R. So here I max will be cancelled, so it can be written as XL upon R. And during resonance condition, the XL can be written as 2 pi FRL upon R, because at resonant frequency this will be the value of XL. So here it can be written as 2 pi L upon R, and we know that the value of resonant frequency is 1 upon 2 pi root LC. Therefore, the quality factor will be 2 pi will be cancelled. Here it is L, it is square root of L. So quality factor is 1 upon R root L upon C. So this is the expression of the quality factor of a series RLC circuit. Quality factor indicates how much amount of voltage is magnified. Let's say, for example, the value of the quality factor is 10. Let's say. That means during resonance condition, what will be the supply voltage? the voltage drop across inductor will be 10 times more than the supply voltage. So quality factor 10 means the voltage drop across inductor will be 10 times more than the supply voltage. And this voltage drop can be used as a source for some another circuit also. So between the resonance frequency, the bandwidth and the quality factor, there is also a relation, and this relation can be written as quality factor is also written as resonant frequency upon bandwidth. So this is also the expression of the quality factor and the relations between these three parameters. Thank you.